The first Fibonacci number is 1, and the second is also 1, and the 8th is 21, and this is rather boring. But what about the pith Fibonacci number, or the eth, or the ith Fibonacci number? Yesterday we recovered that the nth Fibonacci number will be given by this formula, but there's really nothing stopping us from plugging in a z everywhere we have an n, where z is some complex or real variable. Now we have to be careful because one of the components of this Fibonacci formula is a negative number, 1 minus root 5 over 2. So when we exponentiate such a number to an irrational power, that's the same as taking e to the log of that number times whatever power. And of course we can only take the log of a negative number when we're in the complex numbers, so that's why we're doing f of z instead of f of x. So what does this generalized Fibonacci formula actually give us? Well, the half Fibonacci number would be 0.568 minus 0.351i. The pith Fibonacci number would be 2.117 plus 0.042i, and the ith Fibonacci number would be 0.379 plus 0.215i. Those previous results are rather meaningless, but here's something that's actually cool. Using our Fibonacci formula, we can graph the output on a complex plane when we input the whole real axis. If you do so, you get a graph that looks like this. As you can see, we start at 0, but as we approach 1, we kind of dip into the complex plane with a negative imaginary part. Once we get to 1, we have to get back to 1 because the second Fibonacci number is also 1, and how the function does that is it loops through the complex plane going back to 1. Then, as our index gets higher and higher, we loop through the subsequent Fibonacci numbers going above and below the real axis, traversing through the complex plane. So this is the graph that's output when we put the real non-negative line into the Fibonacci formula, but what happens if we put the real non-positive line in? When we input the non-positive real line, we get this beautiful Fibonacci spiral that goes through the complex plane. The negative first Fibonacci number is 1, but then the negative second Fibonacci number is negative 1. Then the negative third Fibonacci number is 2, which is the same as the third Fibonacci number, but the negative fourth Fibonacci number is negative 3, which is the negative version of the fourth Fibonacci number. So we get this alternating Fibonacci sequence that spirals around the complex plane. When we input the non-negative imaginary axis, the output is just these spirals that go around the origin forever and ever. Or as long as I care to check, who knows, it could diverge eventually. And when we input the non-positive imaginary axis, we just get these ridiculously big spirals that pretty much diverge. So yeah, that's what happens when you take the Fibonacci sequence and you open it up to complex values. You get some pretty cool stuff that some might argue is hidden within the encoding of the sequence, and some might argue is just us making stuff up. But that's all for today. Thanks so much for watching and have a nice day.